Something unusual has been unfolding in Earth's skies, and it has been building quietly before becoming impossible to ignore. For weeks now, observers across multiple continents have been reporting an increase in large, brilliant meteors, events known as fireballs. These are not the faint, fleeting streaks most people associate with shooting stars. Fireballs are something else entirely, intensely bright, sometimes rivaling or exceeding the brilliance of Venus, and in certain cases luminous enough to be seen in broad daylight. Individually they are rare. Collectively, what is happening now begins to look like a pattern. At first it could have been dismissed as coincidence. A few striking sightings clustered together, amplified by social media and the growing number of cameras pointed at the sky. But as the days passed, the reports did not taper off. They increased. More videos appeared, more eyewitness accounts surfaced, and gradually what seemed anecdotal began to take on statistical weight. Historical data provides a baseline for comparison. Over the past several years, confirmed fireball events, particularly those with a high number of independent reports, have followed a relatively stable distribution. On average, about 2 such events occur each month, with occasional spikes pushing that number to 5 or 6. These are already considered active periods. But March of 2026 did not follow that pattern. It broke away from it. Within a single month, the number of major fireball events climbed into double digits, exceeding 10 confirmed cases in datasets that apply strict thresholds for inclusion. That alone represents a several-fold increase over the long-term average. And those are only the events that meet high confidence criteria, typically requiring dozens or even hundreds of reports. Beneath that layer exists a much larger volume of smaller or less documented sightings that rarely make it into official summaries. The implication is clear: the sky has become busier. What makes this surge particularly compelling is its geographic spread. Reports are not confined to a single region or hemisphere. They span North America, Europe, the Caribbean, and the South Pacific. In Germany, a bright fireball cut across the sky, leaving behind a persistent glow. In the United States, multiple events were captured by dashboard cameras and security systems, showing fast-moving, concentrated streaks that flare and vanish within seconds. Over island regions in the Caribbean, witnesses describe sudden flashes illuminating the night. Even in New Zealand, reports emerged of a luminous object tracing a path across the sky, its trajectory reconstructed through scattered observations. Some of these events were recorded in detail. Others exist only as descriptions, moments when people looked up and saw something that stood out from anything they had seen before. A flash too bright, a motion too fast, a duration just long enough to register as unusual. When such accounts begin to accumulate across unrelated locations, they form a different kind of evidence, less precise, but difficult to dismiss. Naturally, explanations have been proposed. One of the most immediate involves satellite re-entry. In recent years, Earth's orbit has become increasingly crowded, with thousands of satellites, particularly from large constellations, circling the planet. As these satellites age or lose altitude, they re-enter the atmosphere, burning up and producing visible streaks of light. With the number of satellites rising, so too has the frequency of such re-entries. On the surface, this seems like a plausible cause, but closer examination reveals important differences. Satellite debris behaves in a way that is distinct from natural meteors. Because satellites are already in orbit around Earth, their re-entry paths tend to follow shallow angles aligned with that orbit. They appear to glide across the sky more slowly, often breaking apart into multiple fragments that create a cascading, prolonged display. These events can last several seconds, even minutes, as different components burn at different rates. Fireballs, by contrast, are faster and more abrupt. They enter the atmosphere at velocities that can exceed 100,000 kilometers per hour, depending on their origin. Their trajectories vary widely, sometimes plunging steeply, other times skimming at shallow angles, but always with a sense of speed that distinguishes them from orbital debris. Most appear as singular, intensely bright objects, occasionally fragmenting but typically maintaining a coherent structure for most of their visible path. The recent sightings align more closely with the characteristics of meteors than satellites. Their speed, brightness, and duration point toward natural origins rather than human-made debris. That does not entirely rule out satellite contributions. Some events may indeed be linked to re-entries, but it suggests that they cannot account for the majority of what is being observed. If not satellites, then what? One possibility is that Earth is passing through a region of space with an elevated concentration of debris, a stream of material left behind by a larger object. Such debris fields are not uncommon. In fact, many annual meteor showers are caused by Earth intersecting the remnants of comets that have shed material along their orbits. When our planet crosses one of these trails, particles enter the atmosphere and burn up, producing predictable increases in meteor activity. But there is a key difference here. No meteor showers follow established calendars and radiants. They originate from specific points in the sky and recur at roughly the same time each year. The current surge does not match any major, well-characterized shower. Its distribution appears more sporadic, its timing less predictable. That opens the door to another explanation, one tied to a more recent and less familiar source. In 2025, astronomers identified an object moving through the solar system on a trajectory that suggested an origin beyond it. This object, designated 3I Atlas, joined a small but growing list of interstellar visitors, bodies that do not belong to our solar neighborhood but pass through it, carrying with them material from distant regions of the galaxy. What made this object particularly noteworthy was its activity. As it approached the Sun, it exhibited signs of intense outgassing, releasing jets of material into space. Such activity is characteristic of comets, but in this case the implications extend further. When an object ejects material, that material does not simply vanish. It disperses, forming a trail that can persist long after the object itself has moved on. Depending on the geometry of its path, that trail may intersect with the orbits of planets, including Earth. Months before the current surge in fireballs, some analysts noted that Earth's orbital path would bring it close to the trajectory of this object's debris in early 2026. The timing was approximate, but the window, March through April, stood out as a period of potential interaction. At the time, this was a projection, a hypothesis based on orbital mechanics and observed behavior. Now, with the benefit of observation, that projection appears increasingly relevant. Another piece of the puzzle lies in the directional origin of these fireballs. Many reports indicate that they are arriving from the anti-solar direction, the part of the sky opposite the Sun. This is not random. It reflects the geometry of incoming trajectories, suggesting that the objects are approaching from a region consistent with material that has been influenced by solar gravity and redirected inward. In other words, the pattern fits. That does not mean the conclusion is certain. Space is complex, and multiple factors can produce overlapping effects. But when independent lines of evidence begin to converge, timing, direction, frequency, the likelihood of a shared cause increases. Even so, it is important to maintain perspective. An increase in fireball activity does not equate to an imminent catastrophe. Most meteoroids are small. They burn up entirely in the atmosphere, posing no threat to the surface. Larger objects are less common, and those capable of causing significant damage are rarer still. Probability remains on our side, yet probability is not static. It shifts with conditions. A higher density of incoming material raises the overall likelihood of larger fragments being present, even if the absolute risk remains low. It is not a cause for alarm, but it is a reason for attention. There is also a scientific opportunity embedded in this moment. Events like this provide a chance to study material that may originate far beyond our solar system. Each fragment that enters the atmosphere carries information about its composition, its history, and the environment from which it came. In rare cases, fragments survive the descent and reach the ground, becoming meteorites that can be analyzed in laboratories. These samples are invaluable. They offer direct insight into processes that occurred billions of years ago in regions of space we cannot easily observe. And sometimes they contain more than just mineral signatures. Organic molecules, complex carbon-based compounds, have been found in meteorites before. They are not life, but they are the building blocks of it. Their presence raises questions about how widespread such chemistry might be, and whether interstellar objects could act as carriers, distributing these ingredients across planetary systems. If even a fraction of the current influx is interstellar in origin, then what is entering our atmosphere right now may not be entirely familiar. It may represent a different chemical history, shaped under different conditions, carrying traces of environments far removed from our own. That possibility remains speculative, but it is grounded in known science. For now, the focus remains on observation. Scientists continue to collect data, track trajectories, and compare patterns against existing models. Networks of cameras and sensors are being used to capture events in greater detail, while databases compile reports from observers around the world. The coming weeks will be particularly informative. If the surge in fireballs begins to decline as Earth moves along its orbit, it would support the idea that we have passed through a localized region of debris. If it persists, then alternative explanations may need to be explored. Either way, the situation is evolving, and it serves as a reminder of something easy to forget. Earth does not move through empty space. It travels through a dynamic environment filled with particles, fragments, and remnants of events that occurred long before our planet formed. Most of the time, these interactions are subtle, invisible, but occasionally they become visible, brief flashes in the sky that hint at a much larger story. Right now, those flashes are becoming more frequent, and while they may not signal immediate danger, they are telling us something important. We are passing through something. The question is not just what it is, but what it might reveal.